Hello and welcome to a new video by KStevMath. This video is a part of my Precalculus series that is going through the Math UC curriculum. This is lesson 2, inverse trig ratios. So if you are following along and you haven't watched lesson 1, it would definitely be a good idea to go back and watch that. But here we are at lesson 2. And before I forget, because I often forget, I have a notes page that you can download and print off so that you can take notes along with this, so you don't have to draw the triangles or write down the examples or things like that. And so if you head over to my website, which is linked in the description or should be popping up in the corner here, then you can download that notes page and you'll have less writing to do. But without further ado, let's look at inverse trig ratios. Okay, so I actually take issue with the term inverse trig ratios to talk about what we're talking about today, because inverses are a thing in math and they don't mean what this is saying it means. And so the better word, which I have written here, is actually reciprocal trig functions. And it's better because, one, it's more accurate, because inverse in math is where we switch x and y and look at like a function that's got the x and the y switched, and what does that do to the function and things like that. And that's not what's happening here when we talk about these trig functions. But when we think about reciprocals in math, we're talking about flipping a fraction upside down, and that's exactly what is happening here. So I'm going to use the term reciprocal, or I'm going to try to, because that is the more accurate word. Now, I've got a triangle drawn here. It's a right triangle. These things that are on the screen right now are true only for right triangles, and fortunately we can make a lot of things be right triangles in our life. So that's part of the reason why we like them so much, is that, hey, you got a wall in the floor, that's a right triangle, or a right angle, and so you can make a right triangle, you know, things like that. Now, we have sine, cosine, and tangent were our original 3 trig functions, and now we're going to talk about the reciprocals of those, which are cosecant, secant, and cotangent, and you can see those on the screen here and how you would spell them and that sort of thing. Now, cotangent, hopefully you're like, hey, I bet that has something to do with tangent, because, you know, cotangent, tangent, those are similar, right? And you'd be right. Cotangent is what we would use if we want to use the reciprocal of tangent. So if you remember our acronym that we use, SOHCAHTOA, to remember what trig function goes with which sides. We've got sine, cosine, and tangent. So tangent is opposite over adjacent. Cotangent is kind of this other trig function that is the reciprocal of that, is adjacent over opposite. And then we have these other two kind of new words, cosecant and secant, which are the reciprocals of sine and cosine. And it can be kind of tricky at first to remember these. So here's what I do, is I'm like, okay, I know what sine, cosine, and tangent are. I know which sides go with sine, cosine, and tangent. And so I know these 3 are reciprocals of sine, cosine, and tangent. So if I can just remember which one goes with which, I don't need to like memorize a new acronym. I can just say, okay, sine and cosecant are reciprocals. So if I need cosecant, I'm just going to flip what sine is. Sine is opposite over hypotenuse, so I'm going to flip it, and that's going to be hypotenuse over opposite. And the same with secant. If I want secant of something, I would think, okay, secant and cosine go together, so I'm going to take what cosine is, adjacent over hypotenuse, and I'm going to flip it over. And that may sound kind of complicated, and I do get that. That's kind of complicated. But you should get better and better at it as you go, as you get used to it. One of the things I want to point out that might help you is, so we've got sine and cosine, and then we've got secant and cosecant, and you would think, right, that the two that would go together and be reciprocals of each other would be the ones that like kind of match, as in you would think that it would make sense that cosine and cosecant would go together because they both have co at the beginning, and then have that S word, and sine and secant, wouldn't you think those would go together because they both start with S and don't have the co in front? But it's actually the opposite that's true. And so this is one of those times where you have, if you just remember, okay, it's the opposite of what I think it should be, that sine and cosecant go together, SC, and cosine and secant go together, CS. And then tangent and cotangent go together, and that one's easier because they both have the word tangent. So, what are we going to do with this? Well, we're going to kind of do what we did last lesson, where we look at right triangles and try to find missing sides, or the ratio of missing sides. And we are going to use the Pythagorean theorem for sure this week. So if you don't remember how to use the Pythagorean theorem, there's a link in the description for a video that I did recently to help review the Pythagorean theorem for Precalculus. So definitely check that out if you need a refresher. That being said, it's quite possible that I will do a good enough job of explaining how to use it in the context of this lesson that you won't need to go back and review it separately. But let's see what's next. Example 1. Find the missing side of the right triangle, evaluate all 6 trig ratios of theta, then give the answer in fraction and decimal form. Now, since it's a right triangle, to find the third side, we need to use the Pythagorean theorem. We could actually try to use sine, cosine, or tangent, or even secant, cosecant, or cotangent to find the third side, but since we don't actually know what theta is, it will take us longer, and that's not something that we've actually gone over together recently, so not as good an idea as just plugging into the Pythagorean theorem. So, friendly reminder, the Pythagorean theorem is a squared plus b squared equals c squared, where a and b are the legs, and c is the hypotenuse of our triangle. So here we're missing our hypotenuse. 11 and 5 are our legs of our triangle. So we're going to do 11 squared plus 5 squared, which is 121 plus 25. And 121 plus 25 is, maybe I should write that down, 146. And it's good to be in the habit of trying to simplify our square roots to the simplest thing we can make them. So 2 goes into 146 73 times. Okay, I don't think that is something that simplifies, because 73 isn't divisible by 2, 3, 5, 7, 11, so I don't think we've got a shot at finding something that goes into 73. So that means that this side is square root of 146. Now, in order for us to find sine, cosine, tangent, secant, cosecant, and cotangent, we're going to be from the perspective of theta. We've already kind of identified this as our hypotenuse. We need to identify the 5 as our side that's adjacent to theta, because this side is actually touching theta, right? So it's adjacent. And this 11 is the opposite side. So I'm going to go ahead and write out sine theta, cosine theta, tangent theta, and hope for the best that I have enough room here. And then I'm going to write cosecant, secant, and cotangent. And if I write it in that order, where I wrote cosecant first, then it'll actually help me, because sine and cosecant are reciprocals of each other. So once I know what the answer to sine is, the answer to cosecant is just the flip of that, the reciprocal of that. So then I can write secant and cotangent. Now it can be tricky here because we've got a square root, and at some point along the way we'll probably rationalize, so it can be a little bit tricky in that respect of figuring out exactly what it is that the reciprocal that we want should be. I think you'll see what I'm talking about here in a second. Alright, so sine theta is opposite over hypotenuse, so 11 over 146. Okay, this actually right here is what I'm talking about. I'm going to rationalize this because it's good to rationalize. We do that in math. But before I rationalize it, I'm going to write what cosecant is, because if I flip 11 over square root of 146, I get square root of 146 over 11, and that doesn't need to be rationalized, the cosecant of theta. If I waited until I'd already rationalized and then I flipped it, I'd end up having to rationalize again. So sine theta equals 11 square roots of 146 over 146. It asks for it in fraction form and in decimal form. So in order for us to figure this out, we would get on our calculator and we would do, if you have a TI-84 Plus, even if it's not the new fancy one, if it's an older model, you should be able to press alpha and the y equals button and have this menu pop up. You press enter so that it gives you a fraction, and then we type in 11, and then the square root button, you have to press secant and the x squared, and then we type in 146 over 146, which I had to press down to get to the bottom. Or we could have actually typed it in as 11 over square root of 146. That also would have worked. This decimal, we're going to round to 2. It doesn't say what to round to, so we'll round to 2 decimal places. So this is 0.91. And then we also should probably figure out what the decimal for cosecant is while we're at it. So this would be alpha y equals, and then press enter, secant x squared to get a square root, 146 over 11. Now there's another trick we could use. We know these are supposed to be reciprocals, so we could have taken the 0.91 answer and just done 1 divided by that, and that would give us the reciprocal. But that's whatever. So if we round to 2 decimal places, this rounds up to 1.10. And we have figured out sine theta and cosecant theta. So 1/3 of the way there. Now let's do cosine theta. So cosine is adjacent and hypotenuse, so that's 5 over square root of 146. And just like last time, I'm going to go ahead and write what secant is. It's square root of 146 over 5, because secant is hypotenuse over adjacent, so it's the flip of cosine. And then for cosine, we do need to rationalize, which is going to move the square root of 146 up so that it's next to the 5. And we get 5 square roots of 146 over 146. And then we'll find decimals for both of these. So one of the cool things about a graphing calculator like this is you actually can go back up using the up button and press enter on something you've already entered. And the reason why that's helpful is I've already actually typed in square root of 146 over 146 and just need to change the 11 to a 5. So I deleted one of the 2 numbers in 11 and then wrote over the other one with the 5. If you press the clear button, it's just going to clear the whole thing. So you want to use the delete button when you're just trying to delete 1 or 2 things. So this decimal is 0.41. And then we're going to look at square root of 146 over 5. And again, we could scroll up and use something that we've already done in the hopes that we will have less writing overall, or typing overall. 2.42. Now, depending on, how much you remember from geometry, you may remember that sine and cosine, the way they work, you should always, if you're typing in these fractions, you should always end up with something between 0 and 1. Sine and cosine of any angle is between -1 and 1. So we haven't really gotten to a point where we'd have negative answers, but at some point we will. So all of our answers today should be between 0 and 1 for sine and cosine. The same is not true for tangent, and if you think about what happens with reciprocals and flipping fractions and things like that, the same will not be true for cosecant and secant. In fact, the opposite should be true for cosecant and secant, that they should be above 1 because their reciprocals are under 1. It's kind of a weird fraction thing that's happening. Let's look at tangent and cotangent. So tangent is opposite over adjacent, which is 11 over 5. These are nice. There's no square root. Cotangent is the flip of that, which is 5 over 11. And I don't know what those fractions are as decimals off the top of my head, so I'll do that on the calculator as well. Now, if you do the fraction button here on your calculator and do 11 divided by 5, there's a chance it's going to be very unhelpful. and tell you, oh, that's 11 over 5. So there's two ways to get around that. Either type 11 divided by 5, and then it will give you the decimal. Or if it gave you the fraction, you could then do math and go down to the second one and press enter and ask it to change it to a decimal. Those are your kind of two options there. This is 2.2. I'm going to go ahead and do 5 divided by 11, which is 0.45 repeating. So 2.2 and 0.45. So now, in order to make sure that we've answered the question here, it says evaluate all 6 trig ratios of theta, give the answer in fraction and decimal form. So we have on each of these a fraction answer that is in its best form. In other words, it's rationalized, it's simplified, although none of these we were able to simplify. But if we could have simplified a fraction, we would have, because that's good math to do that. But we have our fraction answers and we have our decimal answers. So I think we achieved what they wanted us to achieve. So this is actually all there really is to this lesson, is we're using these reciprocal functions to find all 6 trig functions and getting in the hang of it. So we've got an example 2 where we'll do this again, and then I've got a now you try so that you can try it completely on your own. Now I want to throw out there, yes, here we're doing a lot on each problem, right? It feels like we're answering 6 or 12 depending on your perspective. We're giving like 12 answers for each of these problems. And so if you haven't already noticed at this point in your math career, we tend to have fewer problems overall when we have things like this, that you have to write more for an answer. So that's the bright side. You're not going to have 20 questions that ask you to do 6 things, or at least not in the same way that you used to. I don't know how many questions there are for this in the Math UC workbook, but there are fewer than what you maybe were used to doing in earlier Math UC books. So that's kind of the bright side. And the other thing is that this is not a thing that we do beyond practicing. What I mean by that is that when we use trig ratios, we pick the best trig ratio and we go from there. So we are doing this thing that happens so much in math education, where we are practicing a skill to build it up, but our practice is being done in a way that does not have a direct correlation to how you would do this in an actual career or real world or modeling situation. Because that's just how it is, that we don't want to make things so difficult when you practice that it's too difficult to get the hang of, and that tends to be how modeling and things like that work. So we're taking this very basic idea of, hey, let's just label the sides and go name all 6 trig functions, even though that's not necessarily something that we would actually do if we were solving a real life problem. Okay, let's look at example 2. We need to find the missing side of this. It's labeled with an L, which I kind of assume that, because I labeled this kind of like what I saw in the workbook, so that probably stands for leg. And then LL probably stands for longer leg, but in case you're wondering, we need to use the Pythagorean theorem here so that we can figure out what the missing side is, right? So we're going to do a squared plus b squared equals c squared, but this time the side we're missing is one of the legs. So L squared, or I could have used a squared, plus 12 squared equals 18 squared. Well, I know what 12 squared is, and I might know what 18 squared is, but I think I'm going to go ahead and do it on my calculator to make sure. 324. So we're going to subtract the 144 over. And get 180. Now that seems like something that will simplify when I square root it. So, simplifying our square root, this is where we say, okay, is there something inside of here that has a perfect square? So I know that 9 goes into 180 because I know that 9 goes into 18. 9 goes into 180 20 times. So 9 is something I can square root and bring out of this square root symbol. But also 20 has a perfect square. There's a 4 here. So in case you haven't done this recently, the way we simplify square root of 180 is we break it down into smaller numbers like 9 times 4 times 5. We can square root 9 and get 3. We can square root 4 and get 2. So those move outside, but the 5 that you can't square root stays on the inside. So this simplifies to be 6 square roots of 5 for side L. And now we're ready to write our 6 trig functions. So L is opposite of theta, and 12 is adjacent, and 18 is hypotenuse. So let's start with sine. Sine is opposite over hypotenuse, so 6 square roots of 5 over 18, which does simplify because 6 over 18 is 1/3. They both divide by 6. So this would turn into square root of 5 over 3. So that's our best fraction answer. Now, if we think about cosecant, which is the reciprocal of this, we would flip it over and get 3 square root over the square root of 5. We could flip over the 6 square roots of 5 over 18, but that simplification with 6 and 18 is going to happen no matter what. So we might as well use this like more simplified answer to turn it over. And then this time cosecant is going to need to be rationalized because of where the square root is. So this is 3 square roots of 5 over 5. So those are our fraction answers, and then we can plug them into our calculator. You don't have to use the fraction button, although it tends to make it less likely that you'll somehow mess up typing it into your calculator. Like I can do square root of 5 divided by 3. I did have to make sure to get out of the square root to do that. This is 0.75. But especially if we're doing something like 3 square roots of 5 over 5, if I don't want to make it an actual fraction, I need to put this in parentheses, this top part. Maybe I don't need to, but it's a good idea. That's not where I want the parentheses. And so I said we need to, and then I backtracked because honestly, this is one of those times where the order of operations of your calculator is tricky. Like I think actually it would do the same thing without parentheses. It's if there was a plus or a minus sign that we would be in trouble. Yeah, this time we didn't need parentheses on it, but if you're not confident about whether or not you need parentheses to make it know what's on the top of your fraction, you should put parentheses around the top of your fraction or around the bottom of your fraction. So this is 1.34. And now we'll keep going and do cosine. Cosine is adjacent over hypotenuse, so 12 over 18. Those both can be simplified by 6, so that gives us 2 over 3. I actually know this fraction off as a decimal off the top of my head. It would be 0.6 repeating, so rounded to 2 decimal places would be 0.67. And then we do secant. So if I flip 2/3, I get 3/2, and I bet you know what that is as a decimal as well, because 3/2 is the same as 1.5, which as a decimal is 1.5. That was easy. Well, easier. Let's do tangent. So tangent is opposite over adjacent, so that's 6 square roots of 5 over 12. Which does simplify like what we've had before, where we can divide these both by 6, so square root of 5 over 2. Then we can get the decimal answer of that here in a second. When I do cotangent, I'm going to flip that over and get 2 over the square root of 5. and that will give me something I need to rationalize. So times by square root of 5 on top and bottom, and I get 2 square roots of 5 over 5. Now let's find those two decimals. So square root of 5 over 2? Yeah. 1.12 for tangent. And then 2 square roots of 5 over 5. Which is 0.89. So there we go. That is sine, cosine, tangent, cosecant, secant, and cotangent of this triangle. Alright, now you try. So do what we did before, see if you've got the hang of this, and this may take a little bit because you're doing 6 trig functions, right? So sine, cosine, tangent, cosecant, secant, and cotangent. I'll just wait here for you and you can start up the video whenever you're ready. Welcome back. Alright, so we're going to do the Pythagorean theorem to find the third side. If you got stuck someplace along the way and had to start up the video without finishing the problem, definitely try to find where, like, the answer to why you got stuck and like how to move forward, and then pause the video again and see if you can get any farther after what you've learned. Okay, so Pythagorean theorem: 8 squared plus LL, so longer leg, 8 squared plus LL squared equals 15 squared. I would rather use A for LL in my Pythagorean theorem personally, because squaring LL looks weird in my opinion. A squared plus 8 squared equals 15 squared. So A squared plus 64 equals 225. So we'll subtract 64 and get 1 borrow 6 1. And I think that might be prime. Nope, well 7 goes into it. I'm just doing the math real quick in my head. 7 goes into it 23 times. 23 is prime and 7 is prime, so square root of 161 is not going to simplify. So that's there's a pro to that and there's a con to that, right? Like, on the one hand, we didn't have to simplify square root of 161. On the other hand, we now have to write square root of 161 a whole bunch. So pros and cons, you know. So theta is here, which means that this longer leg is our adjacent side, the 8 is our opposite side, and the hypotenuse, of course, is this 15. So let's do sine, cosine, and tangent. Sine of theta is opposite over hypotenuse, which is 8 over 15, which doesn't simplify, so we'll just need to find the decimals of this here in a sec. Cosecant is the reciprocal of sine, so we just flip it over and make it be 15 over 8. Let's go find these two fractions as decimals. 8 divided by 15 is 0.53, repeating, and 15 divided by 8 is 1.875. 0.53 and I kind of want to just go ahead and put all 3 decimals here since it did end nicely like that. So as far as rules for rounding and things like that, you first want to verify whether or not the instructions tell you what to round to. That's the first thing to do. These instructions don't tell us though, so rounding to 2 or 3 decimal places is considered best practice. I'd say actually 3 decimal places is better at the pre-calculus, calculus sort of level, but honestly it's just that we need to pay attention to not rounding too early, because that can make us have error basically in our answer. For instance, if we got square root of 161 and immediately found the decimal for that and rounded it to 1 decimal place and then used that to find our other answers, our answers would probably not be as close to the correct decimal as if we just keep using the square root of 161. So that's just a little side note there on why we don't round to one decimal. Let's find cosine. So adjacent over hypotenuse. So square root of 161 over 15, okay, which does not simplify. And then we flip it over for secant and get 15 over the square root of 161. And we will need to rationalize that by timesing by 161, square root of 161 I mean, on top and bottom. So 15 square roots of 161 over 161. So we need decimals for these. So 0.85 for this first one. Box that so we can see it better. And then whoops. Okay. 15 second square root 161 over 161. This would be a bit more difficult to do on your phone calculator, just as a by the way sort of a thing. I keep forgetting what this decimal is, 1.18. So if you are trying to use your cell phone calculator to do this, stop what you're doing and go and download the Desmos app and use that instead. And maybe at some point, if not right now, a video link will pop up in the corner to show you why you should use Desmos instead of your phone calculator to do this. It's a graphing calculator app, but it will also do just normal things like 15 square roots of 161 over 161. It'll tell you what that is in a nicer way than if you had to do it on your phone calculator. Alright, and tangent. Tan theta is opposite over adjacent, so 8 over square root of 161. Now remember that cotangent is the flip of that, and we should flip it before, with this right here, before we rationalize. So square root of 161 over 8. This does need to be rationalized, so don't forget to do that. So 8 square roots of 161 over 161. And let's find these two decimals. If I can find my mouse. Okay. I'm going to go up and just change this 15 to an 8. And get 6.70. And then we need square root of 161 over 8. $1.59. Alright, so for better or worse on this kind of problem that we're doing, the repetition that's happening, if it's starting to feel like repetitive, but you're also getting it right, that's a good thing. That means that you've gotten the hang of it, you're kind of seeing a pattern. So you actually want to be a little bit bored and confident about this, and that will help you know that you've really gotten it. Thanks for watching. That is lesson 2 of Precalculus with the Math UC curriculum, and the next lesson, actually lesson 3, we're going to skip over because it involves using trig tables to find answers to things, and we don't do that anymore. That's back in the good old days. I am tempted to make a video where I attempt to use trig tables just because I've never tried to do that before. I've always had calculators, available to do it. So who knows, maybe we'll see about that. But if you are interested in following along with me in Precalculus, you can check out my website, which is on the screen up above my head, or go to the link in the description and you can see my whole Precalculus course. I'm updating it on a weekly basis. I am teaching it in person as well, but if you would like to just follow along online, there's information at my website to show you how you can do that. Thanks so much for watching. I get a kick out of every view that happens, every subscribe that happens, every like, every comment. So definitely feel free to do any of those things if you'd like to. They do help me out as a aspiring YouTuber, and I greatly appreciate it. So I'll hopefully see you or you'll see me in the next video.